Today we're very pleased to have Professor Qixing Huang here from the University of Texas at Boston. Professor Huang received his undergraduate degree from Huang.
Yes.
With Ximin Hu.
Yeah.
Who I know, and you should all know. And then he received his PhD from Stanford under Professor Leo Bibas. And Professor Huang has done work in all different kinds of areas, too many to numerous, but perhaps is still best known for work in Qixing.
Yeah.
One of the pioneering works in thinking about what we can do with large data sets of chips. Today, we're going to learn about important regularizations or geometry where we use those kind of databases to create 3D shape generation systems. So please put your hands together to welcome Professor Huang.
Okay, thank you. Can you hear me okay?
Yeah.
Okay. So I want to talk about something that my group has been doing during the past 2 or 3 years. Okay, so this is something that I found to be very important. I will continue to work on this because I've got some funding from NSF to support this. So we are in the generative AI era, right? So in my field, also in your field, which deals with 3D data, central topic, the central topic is learning shape generative models, right? Then we have a latent space, and we want to name mappings from this latent space to the space of memory shapes, the space of deformable shapes, and the space of 3D things, right? So those generative models have many applications, in particular, solving inverse problems, image videos. And before the deep learning era, we have non-market results like simple scale, right, value by years. And we have seen a lot of progress, right, in the deep learning era because of breakthroughs in machine learning models, including GAN, VAE, auto-decoder, and very recently, diffusion models, right? So there's a common thing among those machine learning models. They all try to solve the so-called distribution alignment problem, right? We have some training data, right, that defines some empirical distribution. And we have some synthetic distribution defined by the generative model. And we want to align these two distributions. So I should say that this is a very challenging problem. And we have made a lot of progress so far, right? Including the 4 machine learning models as shown in the previous slide. Okay. All right. Of course, those machine learning models have been applied in 3D generation, right? First of all, to do any machine learning, right, on 3D data, we have to solve the representation issue, right? How to encode 3D data in the standard forms like vectors, matrices, graphs, and set, right? So this is a field I think is very exciting, right? Pretty much for all the representations that we in graphics we care about, we have at least one, sometimes we have a few well-known new representations, right? And for 3D generation, we also invented the triplane representation, right? Which bridges 3D domain to 2D domain, okay? So this is very exciting, okay? And it's not finished, right? We still have new representations coming out at CBR each year. But now if you look at 3D generation from the machine learning perspective, okay, then it becomes less exciting, right? Because what has happened so far is that whenever people develop some machine learning models that are applicable in image and video generation, then in the 3D domain, we pick some representation that we adopt, okay? We did this for GAN, for VAE, for auto-decoder, and very recent for diffusion models. Later we'll show, mention another example, okay? So certainly we can just follow this, okay? Because I don't think distribution alignment is solved, okay? recently we have like flow-based method, right? The reactive flow was developed by my colleague, okay? Certainly we can, whenever those things come out, you can think about how to apply them in 3D generation. I don't think this is the right thing to do, okay? Because first of all, if you just do this, then 3D generation is a branch in image video generation, right? Which should not be the case, okay? And another reason is that I believe from the application perspective, image and video generation and 3D generation are very different, right? Because for image and video generation, we care about visual quality. Okay? But for 3D generation, we care about a lot of priors, attributes, right? That we do not talk about in image and video generation, right? So what are those priors? Like for example, if you generate 3D model, one application is in manufacturing 3D printing, not just about like visual beyond AR, right? The 3D content should be grounded in robotics, for example, manufacturing, right? If that's the case, then physical stability is important, right? The shape has to be physically stable, right? Then this is very difficult to do. Okay? We care about topological price, right? The shape has to be connected, right? Should not have a lot of small holes, right? This is also very difficult to do, okay? If you use implicit representation to generate a shape. In many cases, shape is disconnected. It's very difficult to do. And for deforming objects, we care about deformation price. There is some underlying scaling structure, right? Intershape deformations should follow the scaling structure, right? So we have a lot of those priors. If we do generic distribution alignment, right? Network architecture, right? Few of them models priors. The training loss, right? Many of we do not really model priors. Of course, I will talk about how to do that, right? My argument is that generic distribution alignment, if you just do generic distribution alignment, you're not going to preserve those priors, okay? So one argument is that this is because in 3D we have very limited data, right? Very limited data. Maybe we do not have this issue, right? In images or videos, right? Data solve all those issues, okay? But this is an argument for Alyosha efforts, right? He gave a talk at the UT this year. I had a series of debate, okay? So my argument is that this is data is insufficient, okay? You look at the Sora, okay? The amount of compute, right? Amount of data we use to train Sora, right? Is something that we cannot scale up further, right? So it's very expensive. Only a few companies can afford, right? Of course, visually, the videos are very realistic, right? I mean, if you only care about the visual quality, this is not a problem, okay? But now if you look at it closely, right, then you realize that perspective geometry is not preserved, right? We do have perspective geometry, like straight lines, vantage points in the training data, okay? If we use CNN-based architecture, right, to interpolate the training data, right, that is what those geometry models do, right? Under some generic distribution alignment paradigm, like diffusion models, you're not going to preserve very similar geometric structures, right? For example, if you care about using those synthetic video images to do 3D reconstruction, then perspective geometry is very big, right? Of course, if you only care about VR and AR, then visual quality is the most important, right? This is less important. And human perception systems, right? We are not very sensitive to those artifacts. Okay? That is different story, okay? So if those simple geometric structures cannot be preserved by doing CNN-based interpolation, even with a huge amount of data, right? Then more complicated structures, physical stability, topological parts, even more difficult to preserve. Okay. Okay. So in those talk, I'm going to talk about some very preliminary results, right? Enforcing 3D parts. Okay. So I will start with doing so by designing new networks, right? So two purposes. First of all, whenever we are able to design networks to enforce on geometric parts, we should do. Okay, this is the cheapest, right? But on the other hand, this is very restricted. Okay, it's very case by case. It's not very generalizable. Okay, and more generalizable approaches developing regularization models, which I also talk about. Okay. So in terms of network design, I will talk about two papers, okay, which both of them have been accepted this year. Okay, so the first paper is a newest paper next month. We try to use geometric insight, okay, of 3D shapes to design better shape decoders. Okay, it's like DBSDF plus, okay. I'll talk about that. And this work done by my student Anna, and idea come from a faculty at Milan. So Lawyer Argument was the W research. Now he moved to Canada, right? So we focus on deformable nerve, developing a neural network to enforce this kind of one-to-one mapping, right? Which is very important. Otherwise, we'll have ambiguity. Okay, I also talk about that. So the first paper, right? So we want to study, right? Start from DBS step, right? We have an NLP that takes the position input and predicts its scientist value, right? This is very influential, right, in the 3D vision community, right? DBS is a generalization, right? So we optimize the space and we associate with each cell, we have a local MLP, right? For each point, we get the cell, then we use the associated local MLP to decode, okay? This one is better, right, than the DBS there, okay? This is a follow-up work. Now, what we want to do here is to think about such geometric insight, right? So first of all, we know that if you train a DBS-based geometric model, right, to synthesize the collections of 3D shapes, like a collection of chairs, then the chairs have to be consistent oriented, right? The front upright orientation, right? Then it works, otherwise it's small, okay? Right, this is well known, right? Now, if we want to do this locally, right, we have this insight, right? So locally a shape, right? If you learn a little bit differential geometry, okay, I believe many of you know this, right? So locally a shape is a plane, right? We have the notion of tangent plane, right? And also we have the notion of principal directions, right? So if you express the shape locally in the coordinate system defined by normal and tangent principal directions, then it's a quadratic patch, right? This is a data part, like geometric part, right? It's true for any 3D shape, right? Now, the sign function of quadratic patch is a quadratic function, right? So what this means is that when developing the local MLP, if we introduce optimizable local frame, and we transfer the point in the local system defined by local frame, then in theory, we only need a quadratic function to decode the shape, right? Right. So that is the insight, okay? That is the insight, right? Right. It's very simple, okay? Quite surprised that nobody done this before. Okay, so very simple idea. So what do we do, right? So during training, we optimize the MLP, right? The parameters, right? The latent code encodes the shape, right? You change the latent code, you change the local patch, the shape, right? And this patch is encoded by the network parameter, okay? Then we also optimize the coordinate field, coordinate frame inside each local cell, right? Right. Okay. During inference, we have a point cloud input, right? We freeze the MLP. In each cell, we optimize the latent code and the coordinate frame, right? So in deep SDF, we optimize the latent code, right? We freeze the MLP, okay? But we do not optimize the coordinate field, okay? That is a difference. Another difference is that because locally the scientific function is a quadratic function, right? If we just use linear layers, composition for linear is still linear, okay? It's not very good, right? So we have to add quadratic layers in the end, okay? And that improves the performance, okay? Tuning size. Okay, so that is the idea. And yeah.
I had a quick question on the previous slide. So what do you mean by the coordinate field? Is it the field of all these
So
transformations?
essentially, we have a frame inside each cell. Then all the frames together in a coordination space called a field. It's a field defined within each cell. It's not continuous field.
Okay.
Right. It's just like because it defined everywhere in the coordination space.
During training for the shapes, the coordinate system for each patch is
So we
different.
optimize that. We
Optimize,
right.
but doesn't that depend on the tangent plane and the?
So we optimize the tangent plane, and but how to initialize the coordinate field is very important. Okay, so this is will come up next slide. Yeah. So if we do this, we reduce the generalization level by half. Okay, and we reduce the network complexity by 70%, right? So this is easy to understand, right? For example, in image convolutions, okay, we do not optimize the orientations of the neurons, right? So if you look at the first two layers of the image net, right, you have like this edge detector at different orientations, right? So we have to introduce this, right? Because we do not optimize orientation. So here what we do is that we use some geometric insight so that, right, conceptually we only have one edge detector, right, shared by all the image patches, right, because we factor out the orientation. Right? Very simple idea, okay? And how to do that is motivated by the normal and principal directions, okay? So this becomes very important, right? Because if you optimize a coordinate frame, how to initialize the coordinate frame is very important, okay? We have a lot of local minimums. You heard about this, right? So in deep learning, every local minimum is great, right? You do not have generalization. This is our framework, right? Here, if we do not initialize the coordinate frame by doing PCA, right? PCA, the smallest principal component correspond to the normal direction, right? You have a locally plane doing PCA. This is normal direction, right? Initializing this is critical, okay? Right? Without initialization is this number, okay? With a good initialization, we reduce amount by half. Without initialization, some small improvement. Okay? This local minimum is an important issue. Okay, we have to initialize the coordinate frame properly. Okay? This is very important. Okay. Okay, so this is the first paper, right? So right now we are thinking about using this representation to do 3D generation, right? We have a neural representation for each shape, right? We have a voxel-based representation. Each cell we have a coordinate frame, which can be converted into vector, right? And we have a latent code, right? That is a neural shape representation. We can use this to do generation, right? That is ongoing. I do not fund the student. And so, I mean, all the students, they want to do vision stuff, right? And we can talk about this later. Okay. The second paper, I think it's easy to talk about this here, right? Because everyone knows that. Everyone knows nerve, right? So in nerve, right, we have a Holland density field, right? Then we decode, then we do non-real synthesis, right? In the dynamics setting, what we do is that we have a so-called canonical frame, right? We map the observations in each frame to this canonical frame, right? Through some deformation, right? Then what we do is that then for each voxel in the deformed scene, we find the corresponding point in the canonical space. Then we extract that column density field. Then we do non-real synthesis, right? Now, if we do that, this mapping has to be one by one, right? We should have exactly one corresponding point. But if this mapping is not one by one, okay, right? Then suppose it corresponds to 2 points. Then what happens is that we'll do an average, right, of these two, right? Or maybe we pick one of these two, right? Then we run into Barrett's falseness, right? So this one-to-one mapping, which is a geometric problem, is very important, right? So we enforce that, we can get much improved result, right? So this paper studies the issue how to enforce this one-to-one injectivity when optimizing the 3D deformation, right? So that is the problem we are trying to do. So you can do this by adding some regularization laws, analyzing self-intersection, but this is very difficult, okay? So what we want to do this is to enforce the injectivity constraint, right, by developing a new network, right? So in the 3D domain, enforcing this injectivity constraint is very, very difficult, okay? We do not have, pretty much, we do not have any theoretical results to do this. But we have result in the 2D domain, right? So what is the result, right? It's called total embedding, right? So for example, if we have a convex domain, in this case it's square, okay? So we fix the boundary vertices, okay? And we have the so-called Laplacian operator, okay? We fix the location of boundary vertices, then we solve a Laplacian equation to derive location of the interior vertices. So we get, right, for example, we change the location of the boundary vertices, right? We fix the graph Laplacian, we solve the Laplacian equation, right? So this a very beautiful result says that if the boundary is convex, okay, if the boundary vertices preserve the order, okay, no self-intersection along the boundary, then the mesh will not have self-intersection. Okay. Very important result. Okay, no self-intersection. Okay. So this is very good because if we have a mesh for any 3 point, we locate the triangle, then we have the bicentric coordinate, we can define the deformed location, right? So in 2D, we have a very easy way to enforce the injectivity constraint, right? And this is very expressive, right? Because we can preserve the order, we can move the vertices along the boundaries of the square, right? Whenever we preserve the order, we get a one-to-one mapping, right? Now, of course, we can control this by developing a network to specify the location of the boundary vertices, right? So you can think about how to do this, okay? Now if we have this, of course, we do not have this in 3D, okay? This is only true in 2D. Now, how to generalize this idea to 3D? So I think this is a very simple idea and takes motivations from the so-called multiple layers, right, of these networks, right? So what we do is that right? We alternate between different planes, right? So in one layer, we fix one axis, we do the deformation in the plane. In the next layer, we fix another axis, right? We do a deformation in the other, right? It's very simple, very, very simple, right? And because when we, with initial layer, the lifted 3D deformation is injected, right? Then we compose it, it's also injected, okay? Now, so this is, right. And so this is an example, okay? Let me just show you. So usually we use 20 layers, which is sufficiently expressive, right? We alternate between different axes.
How do you pick the position of these layers?
Just randomly.
Just random.
Right. It's similar, right? Because we optimize this deformation for one scene, right? We are not doing this kind of generalization stuff. Yeah. Right. So this is what we get. Right? So it's very expressive. Okay. So visual comparison. I skipped a lot of evaluations, which are not that interesting, but you get the basic idea. Okay. So this is also applicable in 3D shape deformation. For example, when you deform deforming object, organic shapes, how to enforce that of the deformation you do not have this kind of self penetration, right? It's very important. Okay? So by construction, we can do that, okay? Because it's injected, okay? We do not have self intersection. But of course, we need to add some regularization to control the deformation, right? In here, we are enforcing the deformation is AIP as visual as possible. I will talk about that. Okay. Right. Okay. So 2 papers. So what I want to say is that first of all, I think this is important. Okay. But on the other hand, this is really case by case. Okay? Really case by case. Right. It's not really generalized. Right? I think the only field that falls into this category is called equivariant networks. Right? We do have some theory behind that, and different like it's related to group theory, but that is very restrictive, right? So if we think about generalizing equivariant networks to model piecewise rigid deformations, okay, there's some papers from Leo School, but it's very difficult. Okay. Now, so what I really want to talk about is to develop regularization losses. Of course, more expensive, but less constraint, okay, can be applied in a lot of more settings. Okay. So you're working machine learning, you may say that, well, you're just enforcing some inductive bias. This is not interesting, right? So I should say that this is not easy because in graphics, of course, we develop many tools to enforce geometric, physical, and topological priors. The 2 challenges. First of all, they have to be differentiable, right? That kills pretty much about 80% of the tools, right? In rendering, the widely used ones are NERF and Gaussian spread, right? Differential rendering is not very popular, okay? It's very complicated, okay? One reason is the differentiability is very challenging, okay? But that is not the only issue, right? Another issue is that, including myself, right, when publishing a SIGGRAPH paper, right, 10 years ago, right, what we do? We pick 8-12 models, then we show that my approach is better than the baseline. So we publish a paper, right? And if you release a code, right, if the code works for 90% of instances, then it's good, right? People will keep on using it. But if you want to use those tools in the learning procedure, if you have a single failure, okay, then the training crashes, right? We run into this issue, right? So this work, unfortunately, I do not have time to talk about this. So we had this idea in 1-2 days, right? I tell the student, just try this out. It's very easy, right? It took 2 of my students, like in total 1 year, to really make some simple, right, computational topological tools to be stable, okay? So that doesn't crash during the training procedure, 1 year. Okay, I don't have time to talk about this, but this is something, of course, in academia, people do not appreciate. Okay, Xiaoyang, you know that, right? Okay, right. Okay, I don't have time to talk about this. Okay, the second one is that we are doing a high-dimensional problems, right? Diffusion model, distribution alignment, right? We have some machine learning models. How to instill those tools into those machine learning models? Not easy, right? Okay, so this one, I probably still have some time to mention. Okay, now the third one is that the laws should not strongly compete against feed and training data, right? So if you're working in machine learning, you may say that regularization losses try to avoid overfitting, right? So I have a slightly different meaning, okay, which will become clear when I'm talking about this, okay? So here I will talk about solid-based deformable generators. Then we'll talk about mammoth shape, some enforcing geometric physical properties in mammoth shape generation, okay? Deformable object generation, right? So what we want to do here is to train a graph neural network, right? To output a triangular mesh. You change the latent code, you do not change the mesh topology, right? You change the locations of the mesh vertices. So there are many results with 3D comma mesh curve, right? Many, okay? Now, the problem here is that if you just do this generic distribution alignment, right, then you try to interpolate these two shapes. If you have insufficient data, you get a smooth interpolation, okay? But the interpolation does not preserve this bone structure. For example, the length of the leg, okay, is shrink, okay? Okay, we want to address this issue, okay, by developing a better training loss, right? This is motivated from the fact that neural networks are over parameterized, right? They have many more parameters than constraints. How the network is trained, okay, is very important, okay? And this is particularly true for foundation models, right? You do not change the architecture, you change the training target during the fine-tuning stage, right? So what we want to do is to develop a better training loss to really model the intershape deformations, right? To have this result, okay? Okay. So to do that, we need a deformation model, right? So here we use a widely used one, right? ARAP, right? Deformation, right? So within each 1 neighborhood is approximate region, right? Globally, it's non-region. Widely used, and also used in solving numerous problems for images and videos. But our argument is that I think in many vision people, right, this is not my complaint, but that's how I feel that we should teach vision people more geometry, right? Because you look at how they use this deformation, right? So you have a 3D reconstruction, right? Then you minimize the LB deformation between the reconstruction and the template, right? Okay, so if you do that, this is what I mean, right? If you do that, this will compete against feeding the geometry model to training data that has non-rigid shape variations, right? Whether we minimize deformation between this and template, right? Locally, it's not rigid, right? You have this even non-conformal deformation, right? Series, okay? So this is not very good, right? If you just do this, this is a bad regularization model, okay? So what we want to do here is to, first of all, make an analogy to the so-called active contours, right? So how many of you know active contours? All of you, right? I went to MIT, I went to Stanford, okay, give a talk, like less than 30% of students actually know this. I'm very surprised, okay? This should be taught in every undergraduate computer vision course, right? So generative model training, the non-optimization, right? We can generalize this idea to learning shape generative models, right? So we have a data trend, right? So in the shape generative models, you want to feed a high dimensional curve, right? Parameterized by the latent space, two data samples, right? Those data samples define the data trend, right? So we also want to add some regularization because the observation is sparse. So here, interesting is that the regularizations are defined locally, right? So this will have minimal effect in terms of feeding the curve, right, to the observation, right? Some computation was not very serious, right? Okay. So this is a good regularization, okay? Now, we want to generalize this idea to our setting, right? So first of all, the setting is that we have two shapes, right, with slightly different latent code. Right? We have two adjacent synthetic shapes. Now our idea is to minimize the AIP deformation between these two adjacent synthetic shapes, right? Right. So in the active contour setting, we are minimize the length of the curve. Okay? This is analogous to that. What is better, right? We are minimizing some deformation, right? Not just making the curve smooth. Right? We have some better prior knowledge here. Okay. Right. So we want to do this. Another advantage of doing so is that this becomes easy, right? Because in a traditional LLP setting, we have to optimize the rotation, okay? Which is very complicated, okay? But if we only want to do this locally, we can linearize the rotation, right? So in my thesis, I actually did this, okay? So we can linearize the rotation, right? You can learn robotics locally is identity plus a skew symmetry matrix, right? Locally. That becomes okay, rotation. You plug this in, this is quadratic energy, then we arrive at quadratic form, right? In terms of the displacement vector, right? This is something true locally, okay? So in my thesis, I used eigenvectors of this matrix to do shape segmentation to find the rigid component, okay? But at that time, I did not know this can be applied to those shape generative models, right? Right. Okay, so we have this result. Then we plug this in here, right? We arrived at a quadratic energy, right? For the AIP deformation, okay? So let me explain, right? In a batch, we have training instances, right? Some of the training instances. We also have some latent codes, okay? For those latent codes, we also have some of tangent direction displacement, okay? Then we minimize this energy, okay? Right? So J is the Jacobian of the generator, computed using find the difference. This is a sparse matrix, derived from the generative model, okay? Now, okay, of course, we did something slightly more complicated than this, but I want to skip that. So in terms of evaluation, this is something I want to talk about, okay? So we add this regularization loss to three different architectures, mesh generative model. This is the earliest, right? Just a very simple graphic neural network. Does not really model the underlying deformation structure. This tries to model the bone structure of humans, right? Using the mesh hierarchy, right? So we do that without regularization. This is the best. But if you have done so, there's room for improvement by adding regularization laws. It's not that big. Right? So it turns out this one gives the best result by adding regularization, right? Because regularization, right, you define this locally, right? Because like the arterial deformation, if you work with symbol, right, is really approximate, right? There are a lot of violations to that. If we do that by adding regularization laws, we can know that from data, right? It's more flexible. Okay, so this is something I want to mention. Okay, later we extend this to do latent space design. I do not have time to talk about this. Okay, I hope you can read this paper. Okay, so I want to briefly mention this work. Right, so the AIP reg, the first paper, the training data has to be consistently matched. Right, this is too strong. Right, in practice, you really want to know the genetic model from raw data without consistent correspondences, right? So the representation to do that is implicit, right? So this is easy to understand, right? People actually apply this for like deformable shapes, right? Then you quickly realize this, you cannot have post variations, right? You cannot have post variations when geometry models years, right? Because of that, you cannot have like this kind of deformation. It doesn't work, right? Okay. So what we want to do here is to address this issue, right? By adding some regularization losses, okay, to the deformable shape generator, right? So in our setting, the challenge here is that it's an implicit field, okay? One approach is to add some hidden vector field, okay? So what we figured out that is very loose constraint. It's not generalizable. For example, if we want to extend the hidden vector field approach, in fact, it has been applied in deformable. Okay, some of the approaches do that. Whether if we want to generalize this to memory shapes, the locally is a fund formulation, then you have zero constraint in the hidden vector field formulation. Okay. The only way to do so is in a robust manner is to solve the correspondence problem, right? So we have some triangulation of the synthetic shape. Then we find correspondences of those mesh vertices on adjacent implicit surfaces, right? If we are able to do that, then essentially we have a mesh generated local. Right? Okay, if we have that, then we can apply the regularization laws I showed previously, right? Okay, so we need to solve the correspondence problem, right? So we have some mesh on one implicit surface, and we want to find the corresponding locations. Okay. Now, the challenge here is that implicit constraint, right, is one, right? It should be on the surface, but it can load on the surface, right? One strategy is that enforce the correspondence to be along the normal direction, right? So in graphics, and in particular in the level set formulation, this is widely used, okay? But this is a top paper, and they show that, study that, for example, if we have a sphere in translation, okay? If we just enforce the correspondences to be in the normal direction, right? So that is the displacement, right? You do not recover the translation, right? How to address this issue in our setting is to solve optimization problem, right? We know the correspondences should minimize some deformation energy, right? You should have satisfied those constraints. If it's a translation, right? Then the deformation is zero, right? We can recover the translation, right? Okay, so if we do this, we have a closed form expression, right? So we only need to compute this tall matrix. Now for any perturbation in the latent space, we find the displacement in the mesh vertices, right? So this is a parameterization of the mesh locally, okay? So this tall matrix, this is complicated but it only requires computing a factorization of a source matrix, right? This is scary, but computation-wise, not that expensive. Okay, right? So if you have this is becomes easy, right? So we can enforce the deformation prior by treating this as a mesh locally, and we also have answer regularization, right, among triplets locally. So this is analogous to the curvature regularization in active contours, like the gradient of some of the matrix, okay, right? Gradient of like the Generative model, so also second order gradient, okay. All right. Okay, some thought, right? This column is without regularization, right? I mentioned, right, you cannot have large post variation, otherwise it does not work, okay? It's easy to understand, okay? But adding the loss is much better, okay? It's much better, okay? For the interest of time, let me just skip this. Briefly mention this, okay? So what we do here is, if you want to get correspondences, right, we know a Generative model to fit a collection of three shapes, mesh generator, then that gives you intershape correspondences, okay? Like by doing nearest neighbor. Okay, let me just mention this part, okay? So how to do that? Given input shapes, so this is what I just talked about, right? We train an implicit shape generative model to interpolate discrete set of shapes into a continuous shape space, right? Then we use this shape space to find continuous interpolation between a template and all the training shapes, right? It's a continuous interpolation. If you have a path, then we can use this path to do template-based registration, right? Then we have some initial correspondences. Then once we have initial correspondences, we can optimize a mesh generator, right? First initialize the mesh generator using the initial correspondences, then we fine-tune the mesh generator to feed the training shapes. Then we have intershape correspondences, okay? So what I do want to mention that without this regularization, okay, the implicit shape generator is very bad, right? The template-based registration will drift away. It doesn't work at all. It's worse, significantly worse than any baselines. Okay. Fine-tuning is important. Okay, fine-tuning is also important. One story of this paper is that we submitted this to ICLE here. I think 3 viewers really liked the paper. I also like this. But one viewer says you're not doing end-to-end learning, right? So this is not end-to-end. It's not good. Okay. Maybe we made the best strategy of publish the pipeline to do intershape correspondences. If you publish the first component, maybe it's better. Okay, right. Maybe 5 minutes. 5 minutes to talk about this. Okay. Okay. This is a CVPR paper this year. We are trying to do shape generation, right, under the diffusion model paradigm for manual shapes. So diffusion model is widely used, right? But you may have noticed in the 3D generation community, when diffusion models came out, few people followed it, and unless you're doing point cloud generation. The reason was we did not know how to define the so-called probability distribution under implicit recognition, right, which has a infinite ambient space. Now probably we know, right, Gaussian measures, okay, but we did not know, okay. But 2 years ago, this came up, right? So in the 3D generation, you can pre-train a shape decoder, right? You can get implicit shape decoder, point cloud based, volumetric, 3D space, mesh space, right? Whatever you want. Then you fix the decoder, right? Then you do this diffusion in the latent space. pretty neat, right? Then in the 3D community, people feel like, wow, great. About 300 papers in 2 years, okay? Follow this latent diffusion, right? It's simple, right? It will address the representation issue, right? Because in the latent space, it's representation independent. So in the middle is a very strong baseline as Sigurd last year, right? Teaser looks great, but if you don't write code, still like I actually pick those shapes, right? About 30% of the shapes have some issues, right? Which is a decent percentage, not that very big, okay? It's a very strong baseline, okay? But still there are such issues, right? So this is easy to understand, right? Because when training a diffusion model, during training precision, you only use latent codes of 5,000 shapes, which are very sparse, right? Now, this is a very important idea, okay? It's very easy to understand, okay? Suppose you have a pre-trained shape decoder. For any latent code, you can decode the shape into a latent code into a shape. Then you can evaluate whether the shape is good or not. For example, if the shape is disconnected, then you know that when training the diffusion model, we should not sample this latent code, and it's not neighborhood, right? This is something we can do, right? For 3D shapes, we can do more complicated stuff, right? Shape stability, like even like how humans interact with the shape. We can do this, right? So in this paper, we want to train a better diffusion model using this quality check. Okay, that is the idea. Okay, so this is conceptually relevant to the so-called classified guidance or classified theory technique, right? Introduced idea 3 years ago, very recently applied to deformable shape generation, right? Grounded in physics. Okay, but there's certain limitation. First of all, if you do this during the sampling procedure, right? Then you explore some trade-off between diversity and quality, right? GAN has this issue, right? Classified guidance diffusion has the issue is less significant, but still we have this trade-off, right? And also, you need a gradient of the classifier, right? In our case, for example, if the shape is connected or not, we do not have a gradient, right? It's a binary function. So what we want to do here is to focus on the training procedure, okay? Train a better diffusion model, okay? Without using a gradient, okay? So the training loss, we use the EDM framework. Some of you should know this, right? Okay. So this paper has 3 contributions. The first contribution is a way to parameterize the decoding denoise network, right? First contribution. The second contribution is how to determine the hyperparameters. In particular, the constant term in front of, for different sigma, right? Different noise levels, how to balance that, right? Okay, the third contribution is you train a better denoise network, you get better images. You improve the sampling procedure, you also get better images. Okay, so here we want to have better denoise network, right? So we augment the loss using latent codes, right? That pass through the quality check. So in each patch, so we have the training instances. We also have some latent codes that pass through the quality checker, right? To a batch, 2 sources of signals. Latent codes of training shapes, some of the latent codes in which the quality checker have very high score, right? Of course, the question here is how do you determine the weights, how to balance those on a different sigma, okay? So that is one of the key contributions of this paper, right? We did a little bit math. I don't have time to talk about it. This, if do this, this accounts about 30% improvement, right? using the quality checker is important. But if you do this carefully, you can improve further by 30%. Okay. Now, in terms of quality checker, the first thing is physical stability, right? We did worst case structural analysis, right? So this is very different from doing using a physical engine, right? In that case, you need to specify the external forces. Like here, we optimize the worst case external forces. What we figured out that is that if we don't care about the weak visions, right? What this paper do, you can only care about the score, then the eigenvalues of the stiffness matrix is sufficient, right? For example, seventh smallest eigenvalue is 0 is disconnected, very stable, unstable is small, the shape is not stable. Okay. But this is insufficient if a shape has many small holes, then it's still physically stable, right? To address that issue, we actually learn a neural network to predict the physical stability score. Right? You ask the users to label, right? And we cannot avoid this because this is different from GAN, right? In GAN, all the synthetic shapes are bad. In our setting, some of the synthetic shapes are good, some of them are bad, right? We can only do this by user labels, right? Or using foundation models to score a shape, right? Which is the ongoing mode. Okay, so this is the backbone architecture. Quantitatively, we reduce the gap to of a very strong baseline by 20% or 30% in terms of KDI FID score, okay? Which are good, right? It's a very strong base. And we have certain limitations, right? We cannot achieve with them 100% canonical shapes, even by adding a quality check, right? So we actually, of course, we reduce the gap to training shapes by a lot, by 40%. Okay. But the reason is because we do not change the decoder, right? If the decoder is not very good, then essentially we have to learn a very complicated latent distribution, right? Even use diffusion model is still very difficult, right? Of course, the next thing to do is to improve the decoder, which is still ongoing stuff, right? Okay, so that is the end of my talk, right? So I hope I convinced you that 3D shape generating model, right? If you care about manufacturing, care about robotics applications, learn the different from image generating model. Okay? And this is the field where machine learning and computer graphics techniques synchronize. There are many problems to work on, like even doing this on the diffusion models. Okay, it's not easy. Okay, now we are working on improving the quality of the decoder, right, for physical stability. Right? Okay, funding agencies and one student, okay, who is graduating. Okay, thank you.
Thank you very much. Are there any questions?
I had one question about the nerf stuff that you showed, the deforming thing. So the loss for that doesn't have anything to do with the appearance, right? So you don't have like ground truth for the deformation.
No. It's just like enforced deformation.
Right.
The rest is we use a backbone. Basically.
Which means you can do this for any kind of implicitly defined field representation.
Right. We hope that that paper will get some visibility in this deforming field of community, but it has yet to get citation. The last paper already has 5 citations.
It's okay, we've read it. It's waiting long enough, but then what about things will get published? It's like, I have a question. It's a high level question, maybe we can handle it. How big are the arguments that you have with people who say you could just learn geometry in the same way that you can learn images and data?
That is actually a good question, right? Because of course another thing that including myself I've been working on this is, for example, at the object level for 3D shape generation, right? You actually do not need to do that in 3D. The best result we have so far, and it's by a big margin, right? Transformers to predict multiple views, right? The transformers memorize data, right? And they do 3D construction. And we actually visualize the attention map. Actually, the transformers know empirical geometry. Right? It's very interesting, right? The attention map has a perfect prediction of the correspondence, and for example, along the empirical line, right? The variance along the empirical line, right? If you look at my paper called Leap, which I think many people have read that. So we do have some visualizations, right? Transformer, right? So we have this empirical line, the attention map, right? Along the empirical line, we have big variance, right? In the perpendicular direction of the empirical line, we have small variance. So this means that transformers actually learn geometry. Right? Of course, it does not encode geometry, right? But on the other hand, I think this will become difficult if we have very complicated geometric structures. And in many domains, we have very limited data, like in medical domains. Then we have to somehow combine priors when either through network design or regularization losses. So when encoding priors, right, in terms of efficiency, the cost, of course, if you do that at network architecture level, it's the easiest, right? Right, it's very efficient, but it's very limited. You enforce that as a regularization loss, at least you do not need to know the data, right? Or main memory, right? That is at least cheaper, right? Than just using data, right? If you use a huge amount of data, right, you have to know the data repeatedly, right? On hard disk, right?
Thanks, Simon. That's a nice way of thinking about it.
Right.
Yeah. Okay, any last questions? I know lots of you are meeting Professor Huang's substitute. All right, then let's thank our speaker again.